This experiment measures STEFAN'S constant of radiation. A black body is a body which absorbs radiation of all wavelengths which falls on it completely. No radiation is reflected back. If you take a black body at an absolute temperature T, the total energy emitted as radiation per unit time, per unit area of the black body, that is Q, that is given by sigma T power 4. That is the amount of heat radiated by a black body varies as the fourth power of its absolute temperature. This is STEFAN'S law of radiation, and sigma is the STEFAN'S constant, which has a value 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. This is a very important law in physics. Any body is not a black body. It has what is called an emissivity epsilon. The emissivity epsilon of a body is the heat radiated by unit area, ratio of the heat radiated by unit area of the body at temperature T to the heat radiated by a black body of unit area at the same temperature. So epsilon is a ratio. It is a dimensionless number between 0 and 1. A black body has epsilon equal to 1. That is perfect. Any other body has a value of epsilon less than 1. The more highly polished the surface, smaller is the value of the emissivity. Now you take a body of emissivity epsilon, area A, surrounded by surroundings at temperature T2 in Kelvin. You give a quantity of heat Q to this body. The temperature of the body will increase. You prevent convection and conduction. Then the body can lose heat only by radiation. If its temperature in Kelvin, the amount of heat it loses will be sigma into emissivity epsilon into area of surface into T power 4 minus T2 power 4. T is the temperature of the body in Kelvin, T2 is the temperature of the surroundings. So as the temperature rises, the body loses more and more heat till it reaches a temperature T1, when the amount of heat lost is equal to the amount of heat supplied. Then the temperature becomes steady. So when the body reaches a steady temperature T1, the amount of heat supplied Q is equal to the emissivity epsilon into area of surface of the body A into the STEFAN'S constant into T1 power 4 minus T2 power 4. This is my STEFAN'S constant box. The outer box is a stainless steel box, as you can see here, which is covered with a lid. Inside this box there is an aluminium cup which is marked red, and this cup is hanging from the lid by two nylon threads which have very poor thermal conductivity. I put the heater inside the cup. The 100 ohm resistors are fixed on the outside of a Teflon tube which goes into the aluminium cup. The space between the Teflon tube and aluminium cup is filled with aluminium foil, so that heat generated in the resistance will flow to the surface of the aluminium cup. The aluminium cup is painted black, and one junction of a copper constant thermocouple is pasted to the aluminium cup with super glue, which is an electrical insulator. The other junction of the copper constant couple is pasted to the lid of the stainless steel box. The inside of the stainless steel box is also painted black, and the space between the aluminium cup and the wall of the box is filled with loosely packed cotton, so that air currents are prevented. Convection is minimized. The heater leads come to these two terminals, and they are connected to a constant current source in the high current mode. The two switches are up, and we set a maximum current of 200 milliamperes. Do not exceed 200 milliamperes current, otherwise the heater will burn out. The two thermocouple leads come to an RCA plug on the lid of the stainless steel box, and they are connected to channel 1 of the differential amplifier, which reads the thermo EMF in millivolts. You have to wait for 1 hour for this reading to reach a steady value. The reading will keep on increasing, and after 1 hour it will reach a steady value. Then note the current and the reading of the thermo EMF. After noting the current and the reading of the thermo EMF, reduce the current to 180 milliamperes. Okay, 180 milliampere. Now the reading will start coming down. You have to wait for 45 minutes. First reading 1 hour, subsequent readings 45 minutes, till this becomes steady. Then note the current and this reading. You keep repeating this for different currents of 200, 180, 160, 140 and 120 milliamperes. Note the room temperature and convert it to Kelvin by adding 273. That is the temperature T2 of this stainless steel box. A sample set of readings are given here. The temperature T2 of the surroundings, I think that should be focused, okay, is 299 Kelvin. The diameter of the aluminium cup is 2 centimeters, not 2 meters. The height of the aluminium cup 3.3 centimeters, not 3 meters. The surface area of the aluminium cup is made up of 2 parts. The surface area of the cylindrical surface, which is pi d into h, plus the surface area of the 2 circular end faces, which are pi d square by 4 and pi d square by 4. So you can calculate the total surface area, which is 2.7 10 power minus 3 meter square. The emissivity of black paint is taken to be 0.95. The resistance of the heater is 20.1 ohms. The first column of the table gives the current in amperes. What you are measuring is in milliamperes. 180 milliamperes is 0.18 amperes. So you have current 0.203, 0.182 in the first column. The second column gives you the heat generated in the resistance per unit time, Q in watts. That is obtained by taking the square of the current, multiplying it by the resistance of 20.1 ohm. So you start with a maximum heat input of 0.8 watt and then you reduce the heat input. The third column gives the differential amplifier reading in millivolts. It is 1.78 millivolts. Convert it into microvolts by multiplying by 1000. 180 microvolts. Coupled has a thermo power 40 microvolts for 1 degree difference in temperature. So divide 1780 by 40 to get the temperature difference between the aluminium cup and stainless steel box, that is delta T. It is 44.5 degrees. The temperature of this box is 299. So the temperature of the aluminium cup is 299 plus 44.5, that is 343.5 Kelvin, that is T1. Last column gives T1 to the power 4 minus T2 to the power 4. After you make all the calculations, plot a graph of the heat input Q in watts on the y-axis and T1 power 4 minus T2 power 4 in Kelvin power 4 on the x-axis. The 6 experimental points are shown as dots. You fit a straight line to the experimental data. Find the slope of the straight line, which is 1.382 10 power minus 10 watt per Kelvin power 4. Then the Stefan's constant sigma is the slope divided by the emissivity 0.95 multiplied by the surface area, which was a value about 2.5 10 power minus 2 meter square. So that gives you a value 5.38 10 power minus 8 watt per meter square Kelvin power 4. The exact value is 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. We get a slightly lower value because there is some heat lost by conduction. There could be some heat lost by convection. We have minimized it, but we have not reduced it to 0. So the value is slightly low, but it is within 6% of the exact value.